for those who stayed. I appreciate that. So this will be a second talk related to our security project, which investigated security of the digital satellite TV ecosystem. This time it's going to be a little bit more technical, and it's going to be presenting to some other issues. I'm not going to repeat the stuff I said about security explorations, so let me say something about the presentation goal. So we want to continue this presentation and reveal some other information that we discovered when it comes to researching digital satellite TV set-top boxes. We would like to educate you about security risks associated with licensing technology, ecosystems such as digital satellite TV, some insecurely implemented proprietary hardware components, as well as So again, a disclaimer, this stuff is even more sensitive than the previous one. So I want to emphasize once again that this presentation, all information is provided for educational purposes only. We do not encourage or promote. Prohibited. So why bother about content security? So digital satellite TV is these days primarily about content security because premium television networks broadcast and deliver their premium content by the means of satellite TV. Pay TV piracy remains a major concern for many channels and operators, and the reason is because it leads to financial losses in North American pay TV. The security of premium content. So content is not delivered to set-top boxes in clear text. It's encrypted, it's broadcasted in encrypted form. The copper flag and the transport stream packet handler. Usually, set-top boxes use dedicated security chipsets for decryption, for speed, and for security. And when it comes to the key components, subscriber smart card. This smart card holds information about the subscriber's rights, access rights to different programming, different channels, and different. Given content. So when it comes to the control words, which are at the key of the whole thing here when it comes to the security of digital satellite TV system, as I said, 64-bit secret keys used to descramble encrypted MPEG streams. They are used for audio. HBO uses different keys than, for example, Fox. And they are generated automatically by the content provider. They are changed every 10 seconds. Yeah, there are different keys, odd and even keys, and the keys are broadcasted to the client devices in encrypted form, and usually some kind of asymmetric crypto is used for that purpose, and the keys are carried in entitlement control messages, or they contain the and the message format is specific to a different conditional access system vendor. So the PID of MPEG stream carrying given ACM messages can be denoted, can be found by some CA descriptor, which is usually broadcasted as part of elementary streams associated with actually the system that protects the content in a satellite set-top box environment. So it simply makes sure that certain criteria are fulfilled before access to the content, to the scrambled content, is granted to a given user. So this is the subscriber smart card, which holds information about subscribers' access to a given programming. And it holds information to, what programming packages or video, movies, which means paying subscribers can decrypt encrypted programming. So, and this is the set-top box device that asks smart card, give me the control word key for this programming, yeah? And the smart card is gonna release the control word key only if a given user is entitled to watch a given programming. So this is basically this architecture. We got this, again, the scrambled MPEG stream, and we got, as part of the scrambled MPEG stream, we got and smart card is able to decrypt those keys, but the keys which are used to scramble the content are only released by the smart card if the user is allowed to view a given content. So, and of course, when it comes to this model, there are some threats. So the primary threat comes from the fact that all the premium content is encrypted and broadcasted to all subscribers, and there is only one ROC subscriber in your digital satellite TV network. That subscriber can, for example, subscribe to all premium channels and then can start releasing the crypto keys to the scrambled MPEG streams. So, and this is why the digital satellite TV industry came up with some other solution, which is called the conditional access system with chipset pairing. And this solution simply tries to tie control words with means that control words are different for a given device and for a given chipset. So this link is applied between a smart card and a client device. So the illegal content redistribution is prevented because you cannot share the keys which are different for every subscriber. Yeah, every subscriber, every smart card releases different keys to a given set-top box because there is pairing, set-top box and the smart card. Oh, and then here we got those. The pairing is marked with this box, and this is the pairing function. And what the pairing does, it simply uniquely ties a set-top box device and a smart card. And the goal is to make sure that the control word keys are not the same for every subscriber. So when it comes to the pairing function, actually not much is known about it when it comes to different documents. Basically, this is a cryptographically function. It ties a set-top box device and the subscriber smart card. Usually it has this form. So the actual tying is accomplished with the use of some encryption algorithm. And what's used is, in this pairing function, one of the key terms is the control word pairing key. This is actually the key which is unique to each subscriber. And this is the key that makes the pairing function unique for each pair by a digital satellite TV operator at the time of activating a given user's subscription. At the time of activating the subscription, this key is sent to the set-top box device and to the smart card. And usually, for the security purposes, this key is unique to a given DVB chipset. So Conax is one of the leading providers of the conditional access system with chipset pairing. Their solutions in software and hardware, and because of the chipset pairing functionality, they need to have partnership with different DVB chipset vendors in order to be able to properly implement the chipset pairing functionality. And these are some of the vendors like STMicroelectronics, Broadcom, Renesas Technologies, etc. So because Conax wants to make sure that so Conax runs mandatory comprehensive evaluation of all the chipsets that they are supposed to run their conditional access system with chipset pairing. This is done at different laboratories around the world. So those chipsets are then later issued some kind of scoring, and this scoring is certified in writing by the Conax Chief Security Officer. More information can be found on the Conax website, but what I want to show you is that that's the case of Notion company. Okay, so this is going to be about DVB chipsets. So I gave you some introduction to the conditional access system and how the security of content works in the digital satellite TV world. So DVB chipsets actually implement the core functionality which is related to the handling of MPEG transport stream and different audio-video data. So they do the filtering, they do the descrambling, they can do audio and video decoding, graphic display. Implemented a system on chips with different dedicated cores inside. So this is one of the implementations of those chipsets. This is the STI7100 single chips, high definition set-top box decoder. This is actually the architecture of the chip. You can see how many components there are. Yeah, so it's pretty complex system, but that's a chip used in set-top boxes for running code, but also for MPEG handling and descrambling. This is the other chipset we work another generation model of the single chip high definition HITB decoder, a little bit different architecture, but still a complex system. So we worked with these specific devices, which were also showed during the previous presentation. And these were the HITB set-top boxes. All of them were running upon the ST Microelectronics DVB chipsets. So we found out that these were two generations of these chipsets, generation 1 and generation 2. Well, when it comes to breaking DVB chipsets, so actually, we didn't plan this, but at some point of time when we work with the set-top boxes, we just took the challenge and decided to see if something could be done with respect to the security of content by the malware code. And so the security challenges regarding the breaking DVB chipsets are related primarily to the fact that not much is known with respect to how they work. Not much is known with respect to how the engineer, you just got a piece of silicon, yeah? So how to just start working with this? So many undocumented interfaces, unknown implementation of the cryptographic algorithms and keys. So lots of unknown stuff. So it's a pretty challenging thing. So how come? We were able to break a couple of chips. So it definitely took the majority of the 1.5-year time we spent on this project. So this was together and glue together many pieces of information, and we called them clues. And by doing so, it was possible for us not only to discover how certain chipsets work, but we are also able to find security vulnerabilities in them. And of course, we built a couple of tools because, in our work, tools are very important because without the tools, we wouldn't probably be able to finish most of our projects. So some of the common approaches when it comes to working with different implementation. Yeah, so we took some information from data briefs available on that st.com website, and they did contain some generic information about the chip architecture, about some subsystems, some components, and what kind of cores were inside and for what purpose they were used. But actually, there wasn't much. Yeah, so. But something is better than nothing, yeah? So it still was something worthy for us. engineer some device drivers. We had full access to the set-top boxes. So this is why this is the second talk. Yeah, it's building on the previous talk. We had full access to set-top boxes, to the Linux OSs, to device drivers. We started to statically analyze binaries available on these systems. What we wanted to find out, we wanted to find out device drivers that handled control words in some way. Yeah. So we inspected the libraries, we checked different symbols, and we find some clues, some information. The security keys in MPEG describing. So we had GSEC-HAL device driver, SCTKey DMA device driver. They are for different chips, and because the different drivers for different chips because the chips are different. So that wasn't enough because knowing which device driver is responsible for something it just maybe doesn't lead to a lot of clues. So we wanted to find out which function was actually responsible for uploading the key to the runtime analysis engine we implemented on a set-top box. In a set-top box environment, we used our smart card I/O instrumentation functionality, and we simply sniffed for different ECM messages sent to the card. We watched for the responses returned by the card, and one of these those responses were embedding here the encrypted control words, yeah, because we were working with the chipset. The actual API dealing with the control words, we simply started to do IOCTL tracing, and we found out that there were some IOCTLs which were taking the same arguments as returned by the smart card. So by doing this, we simply could correlate this data, and we could find out which API was handling the key decryption and key loading to the chip. So some other very important thing. Although we work only with we worked primarily with the platform N digital satellite, which is called TNK, and that's a service along the major digital satellite TV provider. It provides different set-top boxes, and it also has Conax cards. But what's interesting here with respect to the TNK digital satellite TV, the same audio and video streams are broadcasted to the platform N and TNK subscribers. So, but there are separate conditional access information subscribers. What that meant, it simply meant that we could look up information with the use of pure Java API, and we could find out the identifiers of the streams which were carrying those ECM messages. So we could find the stream for the first one is for the TNK, OB00, conditional access system ID, and the other is OB01, is the conditional access ID for the platform N. Messages, and we started to feed ESM messages being issued at the same time of time. Well, something happens with the projector. So, yeah. Oh no, I don't see a power. Okay, so we started to feed different ECM messages to different TNK cards, and the result we received was that TNK cards were releasing exactly the same keys, two different cards. What that meant for us is that the TNK cards were not using chipset pairing. So they were releasing plain text decryption keys, and we could use the encrypted control word keys released by the main digital satellite TV platform we worked with. I don't know whether I should proceed if there are problems with... You know what? I think it's frozen because I changed the slide and there is no response. The projector is frozen. excuse me, guys, it's frozen. The projector is frozen. I changed the slide. It's showing. Okay, I'll just continue. I don't have a picture here. So one of the next steps, and now I'm trying to tell a little bit more about how the STI 7100 chipset was, broken. So, well, we knew the device driver that implemented the functionality related to the key decryption. This was the decrypt SCK function. By analyzing the device driver code, the binary code, we also find out some meaning of the configuration data. We found out that there are some, that the chip is working in a secure mode. We found out that the chip was not using EAS keys. We find out some information about the registers, the mapping to the memory, because the chip's register space was memory mapped in kernel to the kernel memory. Used for programming a given chip, simply by analyzing the code of the decrypt SCK function. So I just wish it was visible, because now I have a picture. And a picture is like 1,000 words, so. Well, so I don't know what, oh yeah, there is some switch going on. So maybe I'll tell a little bit more about that binary analysis. So analyzing binaries is quite easy when you have symbol information left in binaries, So it probably shouldn't happen if a given vendor wants to hide something, So couldn't be so chosen or giving so much information about the functionality of the code which the function name describes. So we did the analysis of the device drivers, which we found out are dealing with key operations. And we also, by analyzing the functionality of the core key decryption routine, you are able to write some kind of pseudocode. And here I got this pseudocode, and it's really important to see on this picture some kind of, because there is a clue. what you can see here is that also in the code we have that is not working in the secure mode. What happens is that simply the control words are loaded into some addresses. And there was one address which was leaky, and 6100. This is the offset and the chip's I/O memory mapped region, and this was actually the leak. I knew that this was something interesting and a good start. At the offset 6100 were not available for the external world, I should say. So read operation was always returning 0, and any write operation didn't disrupt the MPEG descrambling. So, but we also remember that at the time of the analysis of the device driver, we remember that there was some kind of bounce checking at the device. Make sure that the key indices, the key that were loaded to the chip, were always within that range, 0 to 31 in hexadecimal. So we abused that and we tried that, and it turned out that this was the core of one of the security vulnerabilities. So what we found out is that if the chip, the ST1700, sending direct I/O operations to proper registers, and if the index of the decrypt SCK command was greater than 31 in hexadecimal, we were able to actually obtain plain text control word values at a specific memory offset. So this was pretty unexpected, but we verified this. We verified this because we had access to the plain text control word, because we had control word. So this was actually the vulnerability that did exist and was verified. So this is the formula for the crypto freaks. Yeah, this is the actual, how the cause of the vulnerability. I'm gonna skip this. So, and this is the probable source of the vulnerability. This is the image of the STI7100 chipset, and we think that the bug is here at the CP component, the crypto processor. We think that this is a crypto processor. We can just expect from the location that it's close to the stuff and so on. So that's actually inside a crypto, that's actually inside a DVB chipset. So this was the easy part, and now more difficult part, which is related to the STI7111 chipset. That's more advanced chipset and completely different from the one we broke before, and it used a different SCTK DMA chip component. This chip component was also using one loading different keys to the chip, like control words, pairing key, EAS keys. On the other hand, because the STI7111 was embedded in a set-top box environment, which had a different architecture, more dynamically linked libraries, more modular architecture, it was easier for us to reverse engineer the operation of the whole system. We also had some support for crypto DMA operation drivers, and there are lots of kernel symbols. We had like 680 kilobytes of kernel symbols. So, for reverse engineer, this is like a gold mine, yeah? So we find out by reverse engineering the operation of the system that there are different memory mapped chip regions for different keys. So, and we had some hints in the code when it comes to this. So first of all, we deduced with the help of some kernel and user level library symbol regions that were responsible for the scrambling, that were responsible for holding the scrambling keys. We were also able to find out some information about the region which was responsible for some crypto DMA keys. So those two regions and the symbols that were in the code and the actual context the code was used and how the code was tagged with symbols, it helped us to gather, again, information about different chip regions. Of the crypto DMA operations, the majority of all cryptographic operations, we also reverse engineered that library, but this was crazy work because we needed to go up from the library level down to the device driver level, and then at the device driver level we also needed to see, how this propagates to the chip I/O programming register. So this was all about tracking different values, sometimes single bits, and just to see, how to, program that sort of stuff, how to load keys. So we also wrote some custom Java subroutines, and we did this just because we wanted to make sure that what we are doing with our code, API, and the crypto core library was actually correct. So this was the code for verification of our crypto operations. So another hint, very important, we find out why, reverse engineering the set-top boxes, that there was a clear indication of some key, the SCK key. We didn't know what this is. Secret chip key, which indicated the existence of this key, which is unique to the chipset. And the two places where we confirmed this, first place was at the time of decrypting the bootloader code. The bootloader code was decrypted with the use of this SCK key. We never got access to this key, but we knew that some key was being used by that code. And the other indication was when we analyzed the software upgrade distribution, we found in some binary later, we also find out in the kernel level drivers that actually the STI 7111 chip makes use of some firmware. So, and this firmware, the existence of this firmware was indicated by, a couple of code symbols, data symbols. We even noticed that there is some kind of a initialization routine that writes the firmware code into the chip's processor is running that code. Yeah, we checked some stuff like, MIPS, ARM, the usual processors, but nothing matched this specific processor core. So, well, we find another clue. There was a couple of years ago some European 6 framework project, which basically released a couple of documents and also leaked this information. I basically put all the information, the relevant information that was leaked by, which was used by the SUK and OneSpin companies in this project, and gave a couple of details about it, a couple of information about the features, and maybe not really worthy, but still something that some other clue that moved our research a little bit forward. Later, because we knew that there is some kind of slim core, we found out another project and which had an so there was one function which leaked one instruction format, exactly one, nothing else. So, but this was actually the key point in our research, because from that point we could really move forward. We knew we could find out the actual format of the jump instruction for the slim core. For the processor, we had the firmware for, yeah? But what this line leaks is also the memory addressing, that this is done by word number. So, what we started to do, we started to try to find some patterns in the slim core firmware. So we knew that there is also some get public ID command implemented by a device driver. This command simply returns a chip ID. It needs to communicate with the chip, with the firmware. And we were able to find some relationship between here, the structure returned by a device driver, and the structure and the numbers here in the code. instructions that were putting these words to the output of the device driver. We confirmed that by changing here one story instruction with the other story instruction. So we had another value, not the one we expected. So we knew that this was actually the piece of code that was handling the get public ID command. So, and this was also a very crucial moment in the whole research. So we started to decfeather. What we did, so we knew that we could change the firmware code in runtime. This probably shouldn't happen. You have a secure chip, and you know the secure chip is initialized, and some firmware is uploaded, and some firmware is being run, and at some point of time, attacker is able to inject arbitrary instructions into the firmware coder execution path. This shouldn't probably happen for the secure chip, but let's leave it. So we are able to replace arbitrary instructions, analyze the effect of different instructions execution to the environment. By the environment, I mean the memory and registers. So, and this is how we discovered some other instructions. So, and this is the idea behind this. So we had the firmware code. We knew the piece of code that was implementing the get public ID function. So we simply, we knew the jump instruction format, so we did the jump to the end of the firmware. There was a gap. We knew the store and load instruction because these were one of the first instructions we could reverse engineer. And we returned back to the original code path of the get public ID function. So, and this injection of user code into the path of the get public ID function implemented by the Slim core firmware was at the core of reverse engineering all other instructions of the Slim core. So, and the basic loop and the basic approach we use here is that, if you know to actually reverse engineer all other instructions. Why? Because you can jump to your code, you can store the register contents, you can load another context, you can execute unknown instruction, restore the original context, and jump back to the code firmware path. So by doing this, by experimenting with different instructions, we're able to find out about the format of the unknown instructions which were used in the Slim core firmware we were playing with. So when engineering, this is basically, we started with the load store instruction, then there were move instructions, compare instructions, conditional branching, and one of the most difficult were all those instructions dealing with bit extraction, manipulation, and there was also some repeat instructions, some kind of a prefix which repeated a couple of instructions for a couple of times if this prefix appeared before an instruction. Of course, we tried to reverse engineer only the instructions that were in the firmware code we were dealing with. On here, try to put here some colors. So the move instruction could be easily confirmed by store. If we injected the move instruction, we could see if storing the result of the register value somewhere actually did produce the value which was loaded to the register. Same for compare instructions. What we use here to find out the conditional jumps and compare instruction was that we knew that here there were some values very similar to the values of the commands handled by the device driver IOCTL. So we could compare and conditional jumping sequence. So at the end, this was of course very tedious work. We've encountered many boot ups of the set-top box decoder because if you execute an instruction which isn't valid and or does something which shouldn't be done, there was a reset and stuff like that. So finally, we were able to disassemble most of the firmware code. These were something like 1,400 plus instructions. Only 11. Analyze how the firmware code works. Why sufficient? Well, we were able to discover separate dispatching for crypto DMA, for working with the TKD operations. TKD operations, these are the operations dealing with keys. We also were able to see some patterns which implemented semi-threads or semi-context switching in the firmware code. And this was pretty short for firmware, so we didn't expect even any context switching, but there were a couple of, some key initialization subroutines. So unfortunately, this wasn't enough. You can do static analysis of some code, but always, tracing, runtime tracing gives you a bigger picture. So what we did, we actually implemented some kind of a tracer. Yeah, and it was implemented. Its implementation consists of 2 parts. There was a Slim Core part and there was a Java part. So at the Slim Core part, we are simply doing some kind of binary instrumentation. That's a pretty complex. Then we're trying to notify Java part, now log to the output, the registers, and the actual instruction and stuff. But this worked. And why we did this? We wanted to locate the part in the Slim Core instruction sequences that was dealing with this particular functionality related to loading keys to the chip, the decrypt key functionality. And so here's just a quick look at the the output log of our and we were able to actually pin down the instruction sequences that implemented the loading of the encrypted control word to the chip. So this is the instruction. So we have an instruction that simply puts chip into the triple DS mode. Then we see the instruction that loads a specific internal chip command to the register. We see some instruction that does some kind of waiting. We don't know, but it looks like a waiting. We see some kind of sequence which loads the storing of the result. Of course, all of the instruction opcodes and names are sort of, these are our names. We've never seen any instruction opcode specification and stuff like that. So this is just figured out by the functionality of the instructions. So by analyzing the Slim Core firmware, we also noticed that there are some internal chip commands used by that firmware. These commands to sort of put those commands into separate blocks, because you can see some patterns here, yeah? One block, second block. So it's not like this is the random command space. So, and the most important commands here are those. When it comes to translating the high-level device driver command, which loads the control word pairing key to the chip, this command was used, the internal chip command. And when it comes to setting the encrypted control word to the chips at the Okay, so, well, we started to play even deeper with the internal chip and with those commands. So we wrote this simple piece of code. And why we wrote this? Because we wanted to actually see, what a given command does, what arguments it takes, how it changes the keys, memory, and stuff. So this is our primary code for instrumenting the internal Slim Core firmware. How we could play with this instrumented code. We could simply give some input. We could play with specific commands. We could see, how keys change with respect to different commands. And this was also a very crucial part in this research, because we are able to discover the internal crypto-core command format. So we find out that it's composed more or less of these parts. So we had a target, the target specifying a result should be put, a source from which source a given key, should be fetched for the operation. We had a key sometimes this key was specified as a key slot number, or if value 00 was used, this was the identification of the SCK, this chipset unique key. So basically, we knew the TKD command format. And here's a sample of the operations, those two critical operations we used. And control word pairing key, what it does is simply, it always decrypts register input with SCK key and stores the result as a key at slot 00. The other command also does some key shuffling and some decryption operation. And we confirm all of that with the use of our code, instrumented slim core code, and by playing with different TKD commands. And this is how we are actually able to come up to the security vulnerabilities, because what we found out, of TKD commands, we could achieve something interesting. So here's a step for vulnerability number 1 of STI7111 chipset. So in that configuration, if encrypted control word pairing key is provided as a source, if key is provided as a, if the chipset specific key is provided as an actual key, and the TDS decryption takes place, and the result is stored at key 1, the control word pairing key is decrypted with that key. So in the other step, what we did was we used that key from slot 1 to decrypt our encrypted control word value. We use another command to provide another configuration for the registers and for the operation. But as a result, we are able to store the plaintext value of the control word at some other key slot register. And the most interesting part was that this key slot register, so those marked in red were not accessible for reading. So that's a formula for crypto people, you know, of the whole attack, how this worked. And this was not the first vulnerability. The second one vulnerability, we find out that it's possible to actually obtain the plaintext value of the control word pairing key. The actual pairing key that was pairing by the means of cryptographic function, the chipset and the smart card. So we find out that, you know, we could decrypt the control word pairing key into the inaccessible key stored at key slot 0. That's the default location for the control word pairing key and the STI7111. And in step 2, what we simply did, we simply re-encrypted the result obtained before to achieve the plaintext value of the control word pairing key. And it worked. We verified this. We simply implemented the code that was re-encrypting the values of chipset, and the scrambling operations simply work. So that's actually the second vulnerability regarding the STI7111 chipset. When it comes to the location of that vulnerability, there are 2 bugs, and it's probably somewhere here. We are not sure, but this is the block of the chip that seems to be doing the decryption and, you know, the scrubbing and stuff. So, okay, I'll just maybe skip that slide. So, proof of concept code. When it comes to this security vulnerabilities, it was part of this main code we implemented for the malware operation in a set-top box. So our proof of concept code actually worked in a client-server architecture. We never mentioned that. This is the time to mention that. So we had a client, a backdoor or malware client on set-top box devices. We had some kind of a, you know, backdoor server, and, you know, the different client set-top box devices could communicate with the backdoor server. So functions, we are able to definitely obtain plaintext value of the keys used for the decryption of encrypted digital satellite transmission. We are able to send these keys over the network to other systems and use these keys to decrypt the encrypted content. So we're also able to actually decrypt video on demand stuff, and How this was done, I'll just mention in a moment. So here's the proof of concept we conducted. So we had a set-top box here. This was STI 7100 chip. Here we had a set-top box with STI 7111 chips. So different chips, different set-top box decoders. From this set-top box decoder, we extracted plain text control words for premium programming. We sent them over through our ACM server, through our backdoor server, and this backdoor server simply forwarded the keys to this set-top box, because this set-top box should use the keys received, and it was able to actually decrypt the content. We saw that content more. We even did a capture of that content on that decoder, which proved that everything worked fine. So the other functionality related to the proof of concept code is this video on demand sharing. We are able to use the ability to extract keys, plain text keys, protecting the on demand, because in the environment, in our target environment we worked with, the content was stored on set-top boxes. This is a push video on demand. So the digital satellite TV provider was pushing the content in encrypted form, different movies, to set-top boxes. They were there, stored in the hard drive, but encrypted. In order to simply view them, the control word keys were required, and the control word keys were released only if proper access rights were received by the smart. We were then, during that time, we had access to the content. We were able to decrypt all of the control words which were protecting the movie. And after the period of the rental period, we were able to share the control words with the other decoders, or we could actually use those plain text control word values to descramble the movie. And this was past the rental period. And this was okay. So coming up to the summary. So when it comes to the STI 7100, STI 7119 security vulnerabilities, so the fundamental question we've been asking ourselves is, how come these issues were not discovered before the market release? So ST Microelectronics, that's a major silicon vendor. So definitely #1 in Europe when it comes to the release of the different chips to the market. From Wikipedia. There was this Conax security evaluation, those rigorous security evaluation done for different security chipsets, and it also wasn't spotted. I don't know what kind of information is provided to Conax when it comes to evaluating stuff, whether they full information or just some data briefs. But if they did have full information, this should have been spotted in some way. So we've never received the actual scoring that were assigned to the chip by Conax. This was not disclosed by any other vendor. So when it comes to the impact, so we didn't receive information from ST Microelectronics, and this is the DVB Chipset vendor to our impact inquiry question. So this is basically the sentence that summarizes the response of the company to our inquiry. So we tried to do the impact estimation upon publicly available data. We found the following: the available document by some ST guy, and apparently the cumulative MPEG-4 shipments till year 2008 was more than 500 million chips. So these were set-top boxes, these were digital television sets, DVD, Blu-ray players, because I didn't mention that before, that chips like STI 7111 is not only used in set-top boxes. And the internet. So ST is the #1 when it comes to H.264 market. So it has about 68 of market. It had about 68% of market share in year 2008. So it has customers from all around the world, some of them majors. So, well, but we still don't know, yeah, how many of these chips are out there which are vulnerable, who is using them, which set-top boxes are using them. To summarize this presentation. So what we were able to accomplish, this was definitely the first successful attack against the implementation of a Conax conditional access system with chipset pairing. We didn't break the Conax card. We didn't show that the card is vulnerable, but we did break the implementation of the Conax system in this specific environment of the ST microelectronics chipsets. So satellite TV set-top boxes, those that we played with, that I talked about in the first presentation. So we broke security of dedicated DVB chipsets. STI 7101 was probably had more serious bugs because we even were able to extract the plain text control words pairing key. So definitely one could start asking questions, you know. A dangerous concept, it might look like a dangerous concept. So it's really a little bit shocking to see those kind of issues being, you know, found in a silicon. Yes, some kind of out of band, some kind of design issues when it comes to shuffling of the keys. So there is definitely the need to improve security and evaluation processes by the silicon and conditional access system vendors. We hope that, you know, there is this will be used by the companies from the ecosystem to improve security of their products. So there's definitely the need to tighten set-top box security, which rely on vulnerable DVB chipsets. We don't know much about how many of them are there, but you know, in order to actually make sure that the issues are not so easily exploitable, the primary thing is to make sure that set-top boxes are not so easily hackable. And I also because you still need to get access to the set-top box. You need to completely break security of a set-top box. You need to get kernel level access. You need to get access to the chipset, and then maybe you can start playing with something. So I think that basically that was all. I am happy that I am not past the time. So thank you very much for attending this talk, and I appreciate that. You know, this was 2 hours. Any questions? I am try to answer them.
Question is, one of the reasons you were able to hack the system is because there were 2 implementations in parallel. One which did use the chip card and set-top box key cards. Is it then the responsibility of the vendor of the crypto system to be sure that all its buyers are using the system correctly, or is this responsibility somewhere else? So if you sell a crypto system, some of your customers employ it wrong, and then everything is at risk.
Yeah, so you're probably asking about this to play with different commands, with keys, and even if you were able to see some values somewhere in the chip's I/O memory mapped regions, we wouldn't know what this is. But we knew because we had a reference value from the other, you know, sort of parallel conditional access system which used plain text control words. So this was probably this shouldn't happen. Yeah. I think, well, I don't know who actually was responsible for the actual deployment of the conditional access system. I expect that it shouldn't be possible to have reference plaintext values for the same encrypted content at the same time you have a system you try to make secure. If you have a digital satellite TV platform which you try to make secure, you implement advanced security mechanisms such as why do you have a couple of channels and some other service being offered to the market where you simply have those keys being available in plaintext? Yeah, and not for the like really premium content. Yeah, because the TNK service was this was like a prepaid, like with 20 channels, maybe something like that. But still, the key issue was that we had as a reference value every 10 seconds. At one point we had a text value, and then looking into the chipset memory, playing with the chipset, it was easier for us to find the results of our operations, because at some point of time we find out, hey, here a plaintext control word value popped up. Yeah, so probably actually this service should be implemented in some other way. Yeah, maybe, but probably this is the matter of saving the bandwidth. So you broadcast one channel, and this is actually one content being broadcasted with the use of some keys, and then you have different conditional access systems which are able to decrypt this, because this one content is being used by different digital satellite TV platforms. You can have Conax, you can have IRDATO, you can have NDS, and different crypto systems. So this is well, it really depends from the context. In this particular context, this happened to be useful. Yeah. So they tried to limit values because the channels which were available to the market and the plaintext keys were not really quite like premium. Maybe, yeah?
I have two questions.
Yeah.
First, on the 7111, after all the reverse engineering was complete, were the attacks, did you have to change the firmware for the attacks, or were the attacks...
The second one was the firmware.
7111.
Yeah, that was the key part. Yeah, we needed, without the ability to change the firmware, we actually wouldn't be quite able to execute any slim core instructions. So we were changing firmware. We were hijacking the code path of one function. We're injecting our code sequences of our instructions into that code path in order to see what happens.
Right.
That was the key part, and it probably should one be able to actually change the firmware of some internal crypto core in runtime, yeah, after the initialization.
I understand. The question is, let's say you had some kind of instruction set guide to that slim core that you reverse engineered very brilliantly. Would it be able to mount the attack without the ability to change? Let's say they did have a secure bootloader and you couldn't change anything, but you did have the
that information, or what I'm not sure understand. I'm not sure if I understand your question. Yeah. So
maybe it is convoluted, so I'll wait for later.
Okay. Yeah, I of course open if you would like to ask me some other questions. I am available here at the premises of the conference. So, well.
Yeah, we're actually out of time for questions.
Yeah. So thank you very much for staying so long. I wish you a great evening, and you're welcome.
Technical stuff.
It's okay.
My apologies for that. For the people who are over here, I'm sorry it happened like this today. Today we're going to work with the technicians to fix this problem because somebody called Murphy came in a few times. My excuses for that, and we will fix it. Thank you very much.